demonstrated that we could glue it together properly, so we'll keep the fingers crossed. As far as I know, it's the first strong Yaffe Trap that's been built that way. We're searching for antihydrogen ions. I'm not going to talk about that so much. There the idea is that we could, here's just the one antiproton signal so we can do it. Well, okay, and it's moving along. But the basic, we did this years ago with antiprotons. Here the idea is to look for the anti-H- or the anti-H2+ ions, okay, because we can do that with one particle sensitivity. That's just beginning. It's not a real high priority for us, and we're going to see where that goes. Okay, now we're trying now to do this experiment, as I said, with bigger plasmas and better sources. Okay. Now the summary here is that really much has been accomplished, but much remains in the antihydrogen business. I've been saying that for a long time. I would say we keep making steady progress. Our plasmas are much better characterized right now. Okay, we understand much better what we're putting together. We can measure the temperatures much better. We have hugely more particles and so that we can do. A side experiment is we're trying to measure the antiproton magnetic moment. There we're building on the success we had here at Harvard in measuring the electron magnetic moment to 3 parts in 10 to the 13 and getting the fine structure constant measured very accurately. There's a double trap over at Harvard that has 1 proton in it right now, and I don't have time to talk about it, but we hope that we can eventually probably improve on Dan Kleppner's measurement of the proton magnetic moment by an order of magnitude or so, but that's not really the point. The real point is we can probably improve on measuring the antiproton magnetic moment by a factor of 1,000,000 or more. The trick is we want to observe a single proton spin flip, okay, in a non-destructive way. Now we observe single electron spin flips, but a nuclear magneton is 2,000 times smaller than a Bohr magneton, and that's the challenge of the measurements. Here's a signal from 1 proton. The green line shows the sensitivity that we think we have. Statistically, we have it, but this doesn't tell the whole story. This is these are line width measurements, and what we get is a slow drift, a wander around of this frequency, which is bigger than this by about a factor of 2. And so we're close, but it's not working yet. Okay, there's my summary, and I'm going to quit here and ask Andrew to come up and just finish off for a few moments. Okay, the antiproton and hydrogen update. I went through all of these points. I won't say them again. Andrew is going to talk about the possible use of optical half-cycle pulses to de-excite Rydberg antihydrogen, which is an effort taking place in his lab.
Well, I'd like to thank the organizers and Jerry for giving me a little bit of time to talk about the work I'm doing in my lab, which is down the road, actually on the other side of Cambridge at the Roland Institute. And I've done this with sort of 2 postdocs. Pankaj Mandal is there in my lab right now, as well as Karush Afrashe, who was there before. And we're looking at ways, because of this antihydrogen right now is made in this huge, as people have talked about, in a huge range of states, and ionizes over sort of a factor of 10 or more in an electric field. So there's an issue in how do you de-excite this and get it down to the ground state in order to be able to trap it and study it. It's clear that you need some kind of state-independent method. There's no way you're going to be able to pick out states in here and get any kind of reasonable fraction de-excited. And so there's been a couple proposals recently in theoretical that they use the idea of using short unipolar half-cycle pulses. So these are very short relative to the orbit time, and rather than any kind of resonant de-excitation, you're actually kicking the electron around. And if you do it right, at least theoretically, you can de-excite atoms and drive the population around. The issue is that you need a pulse that's shorter than the orbit time of the electron, or positron as it may be for antihydrogen, and that's in the sort of timescales of 20 to 100 picoseconds for these kind of states. There's been a lot of work on this in terms of using single pulses, but the question is, can you extend it to a pulse train? It's been demonstrated by the group at Rice and Bergdorfer's group that you can do it for high states of around n equals 350 or more, but that you can do it because the orbit times are in sort of nanoseconds. You can do it with electrical pulse generators, but that technique fails when you want to get down into the picoseconds orbit times. So we've started building up an apparatus that allows us to do that. The idea is to use these photoconductive switches where you basically on some kind of semiconductor fabricate a couple strip lines so you can bias it. If you now pump that semiconductor very fast using a femtosecond oscillator, in this case we're using gallium arsenide, so it's nicely matched for the band gap, with a TISAF femtosecond oscillator, it becomes conducting. When it becomes conducting, you have a current surge which radiates, and you get something that looks like this, which is primarily unipolar because there's an asymmetry between the excitation up to making it conducting, as well as the carrier lifetime, where we've chosen a semiconductor that has a very long carrier lifetime in the orders of hundreds of picoseconds. And that makes you have an asymmetric field pulse that has sort of a width on the scale of a picosecond. And you can have fields, in this case, for a high repetition rate oscillator around sort of a kilovolt per centimeter, or in our case, around 500 volts per centimeter, depending on how well you're optimized. We then use just a sort of a standard trap, an optical trap, just modified to have the terahertz optics, which requires using plastic lenses and some other techniques, because you're dealing with very broad bandwidth pulses. They actually have a center bandwidth of about a half a terahertz and a center frequency of about half a terahertz and a bandwidth of about a terahertz, which means you have lots of issues with dispersion and things like that, where you have to be careful. And so we've arranged it so both the low frequency and the high frequency components have a focus right at the center of the trap. We can then detect these pulses, which is what you're seeing over here, just by using this process in reverse, where you make this semiconductor conducting and just measure the current. And you get a signal proportion of the derivative, and that's what this, and then we take the derivative, and that's what this black line is. And so the typical experiment is basically you start off, you turn the half-cycle pulses on because the rise time of our pulse generator that's biasing this thing is around 20 nanoseconds, so you'd get a couple weak pulses if you turn it on after the excitation, so we turn it on before. You leave it on for a while, turn it off, and then basically do your ramped field ionization to determine the states. And the idea is if you keep this ramp at the same time, you get rid of any kind of other effects that are happening inside this plasma due to not plasma, but gas of Rydberg atoms, in things like black-body transitions or collisions or other effects, and mostly are just looking at the effects of these half-cycle pulses. And when we map that out, we get something like this. This is actually the raw data. So we start off, and sort of in this case, we've excited up to about n equals 50 or so. We then watch as we start applying pulses over about 150 microseconds. So you get at 80 megahertz repetition rate, you get something like 12,000 pulses. And we see that we're actually getting to the point where we can slowly field ionize, but we're also driving some population off to these higher ionizing fields, which means a lower end state. You can map across to end states just by using the fact that we've measured that we actually are primarily exciting red Stark states, and so you have a pretty clean mapping. And what's quite interesting is that actually, because these red Stark states are effectively one-dimensional, you can actually make an analytical model of what this impulse does in a single case, and then just apply it. And we get very nice agreement with a very simple model with one basically free parameter of what the impulse is, and suggesting that we are actually driving about 10% of the population down by at least n equals 10 down in here, and we can map across. We can look at this a little better and see that this agreement is quite nice. This is actually what this model looks like. You end up with a little bit of a mess, but in general, for the impulse that we can generate, which is about 8 by 10 to the minus 5 in atomic units, you get about 1% probability of transitioning up or down, and it's slightly asymmetric. And what's very interesting is that by using, in this case, we actually are not varying anything in terms of other than the initial state in terms of the model. The model is the solid lines, the experimental data is the black lines, and these are basically showing the amount of population that ionizes at a field less. So it's the field at which 10% of the population is ionizing, 50% of the population is ionizing, and 90% of the population is ionizing. And we actually get quite nice agreement even as we change the initial conditions until you get to sort of these lower line states where this 1D model starts to break down, as you would expect. The other thing that to point out is this actually, and I haven't plotted this, but we in this talk, but we also get a very nice agreement when we change the amplitude of the half-cycle pulses and just get the, and so there's no Fourier parameters, and this explains quite nicely. The one interesting effect in this is that this model actually is a transition amplitude. It turns out that we basically see decoherence on the time scale of about a single pulse in order for this model to work. What's driving that is not entirely clear. Possibly the polarization of these pulses is perpendicular to the quantization axis set by a sort of a static clearing electric field that's being applied on the field plates at all times. And so it's quite likely we're driving sort of primarily perpendicular to the momentum of the electron, so that there's minimum amount of energy transfer, but you are messing with a phase every time you kick this electron. So in conclusion, we've demonstrated that we can have over 10% of the population change by about delta n is less than delta n greater than 10, dropping it down. That's equivalent to a sort of a factor of about 3 reduction in the radiative lifetime for a completely L-mixed state. And what's interesting for antihydrogen is that because we're sort of on this exponential tail, that actually results in sort of almost or at least an order of magnitude, if not more, increase in the amount of trappable population that will de-excite down to the ground state before it reaches the wall of the trap and annihilates. As I pointed out, the model based on these 1D atoms works quite well, and we actually explains the basic features, both the amplitude dependence as well as the initial state. It fits very well and with no free parameters. And then the future improvements are quite promising. If we manage to reduce the fast timescale decoherence, you can start doing things where you actually trip the repetition rate of the pulse train, and that actually can direct the population transfer rather than having this diffusive population transfer we've demonstrated. You can either drive it up if you slow down the repetition rate of the pulses, and you're just basically driving the electron and causing the electron or positron to follow that repetition rate, or you can drive it downwards by increasing the repetition rate within an experiment. And so that's where we're kind of going.
Questions for Andrew or Terry? Yes?
Andrew,
Yep.
in the weak field regime that you're working with the half-cycle pulses, it's not clear to me that it matters that your pulses are really half-cycle. Basically, in fact, the half-cycle is bad if you're in the weak field regime, because it actually reduces the amount that you can drive down, because basically you tend to kick things out instead of
although we actually don't seem to see much field ionization at all, real in terms of like that kind of kicking. And
there's an A-squared term in the interaction which is not there if you have a full cycle pulse.
Right.
And that always increases the energy of the electron. So that's something that actually is tending to bring things out. So if you had a full cycle, it seems to me you're actually better off than if you have a half cycle.
I guess the question is how much of that average is, when you hit that, it might be better. We actually are largely more towards a full cycle just because of the fact we're in these small gaps. We're definitely less asymmetric than what you can get in the large aperture style. So that may explain some of what we're seeing. Although actually, if you do the calculation, the momentum that we're transferring based on our measured thing is very close to what this model is sort of suggesting. So some of that it's not entirely clear that we're that far off this impulsive approximation.
Other question there?
So I have a question for Georg. So regarding this temperature, the low temperature of your antiprotons. So as I understand,
it was an electron so far.
yeah.
But in principle, the antiprotons, when they're in there, should cool.
Yes, so then the idea is to have them that cold. So, but then if I didn't miss anything, so then the antiprotons are sitting in the sidewalls, so having this 1 Kelvin temperature in the best case now to bring them in touch with the
that's what we've been experimenting with, and I would be lying to say I understood all of what's happening there. It doesn't seem to work as well as we would like. But basically, what you'd like to do is you'd like to cool the antiprotons, or you'd like to, and then remove the electrons, or leave enough electrons in there to keep it cold. But then you have to raise their energy if you're going to make them interact. And we've been doing that by ramping down the central well potential so that they come in contact. Okay, that doesn't give you a really long time for them to interact. Okay, and so the other thing you can do is you can try and raise their temperature and then go through it, because in some sense the temperature distribution of the antiprotons then shouldn't matter. Because if you bring the positron well down through the antiprotons, which are up some height in the side, then the hottest ones of the distribution are not hot with respect to the positrons. So you get a kind of phase-space compression that way. Okay, and so that's what we've been experimenting with. I would say it's extremely important to get a really good handle on the plasmas and their temperature and their geometry to do that. And we're making steady progress on that. I wouldn't say we've arrived at this point. Okay? Yeah.
I sort of, when you're trying to mix the antiprotons sort of through the positrons that are up higher, it seems like it might be better to have fewer antiprotons, because the antiproton-antiproton collision is going to sort of take that translational kinetic energy that you're sort of sitting in this deep well and turn it into cyclotron motion, which you can't get rid of. So it seems like it might be better to not have a million p-bars.
Well, it's not so good if you want, if you have an inefficient process, okay? But I think that because you just won't have enough to count, okay? But basically, I think that the antiprotons, once they go into the positron plasma, if we can do it right, in principle, we should be able to have quite a few collisions inside of a substantial positron plasma. Okay, and so there's some cooling that can happen in that way inside of the positron plasma. Okay, you're talking about if you take the antiproton and it goes back into the sidewell, okay, and then it can make a collision. The amount of axial energy it turns into cyclotron energy will be of order at most the axial energy. And so that can be, that kind of can be cooled in the positron plasma.
But that's really high, right?
It can potentially be high, that's right. So you have to rely on the positrons to do the cooling or the electrons in the sidewell to do the cooling. That's right. By themselves, the antiprotons don't cool themselves at all. Yeah.
Tom?
Question for Andrew. So what range of frequency chirp in this pulse stream you need to be interested?
Well, if you really need to match it to sort of the orbit period, so it's really large factors in some sense. In the end, probably you almost need to start getting into sort of factors of 2 type things. One issue is that the repetition rate of the pulse train is much slower than the orbit period, so you're sort of on a very low subharmonic, and so it's not clear. There's some issues on coherence and things like that as to how effective that is on that scale. So that does reduce how much you have to chirp it as well, but at the same time, it's this n-cube scaling does hurt you pretty badly if you want to be able to change it a large way.
Are there any more questions? Yeah, maybe one last one. So, do you expect so that this pulse train method directly transfers into the chaotic dynamics of the strongly magnetized?
It's not clear. I think it'd be quite interesting because you're it's a different way to probe those dynamics. I think in the axial, yeah, it's clear that there's not much difference there. But it's a question of, the transverse I think could be very different, and it's going to be interesting to see whether it does some kind of drift motion across the field or what exactly it does.
The metrics are very different, right?
Yeah.
So
it's a very
working on a highly degenerate system, and
But Tom's done the experiment with microwaves.
But not in the microwave.
Not in the magnetic field.
right, and
The magnetic field,
could
yeah.
change a lot of things.
Oh yeah.
Okay, so then let's thank all the speakers again.